welcome to Feed System Design, second, I think, of our lecture series at LPL. A little bit about me, because we have a lot of new people here. My name is Mike. I went to undergrad in the UK, University of Manchester, got my Masters in Physics, then came here to the ASD department and got my Masters there. In this May, I graduated. So for 2017, I was one of the two leads and also like the lead technical engineer. So me and John, the other guy in this picture, led the lab in 2017. I played a leading role in the design of Hydra, which started around February in that year. Then I designed and built the water test stand. That was between June 2017 and this summer, June 2018. And then me and John designed the Jesse and James engines last semester. He's going to be doing an engine design lecture pretty soon, I think. I don't know what the date is yet, but that'll be soon. And then I was the lead author of the paper that we submitted to the IAA on the water test stand. Me and Honzo wrote that. And then I co-authored the Hydra one and John's objective and strategy paper as well. So if you haven't read them, I definitely suggest doing so. And then right now I'm at CERC and I'm the TT&C lead for the CubeSat project that we're doing there. Some contact info if you ever need to get hold of me. So today, this is like a content pretty much for reference, but like a scope of these slides. So I'm just going to be covering pressurized gas propellant feed systems, so pretty much what we do at LPL. That's like pressure drops and losses, hard lines, flex lines, component sizing, pneumatics, regs, valves, filters. But I'm not going to cover like engine cycles, obviously not turbo machinery and pumps or anything. Not going to be going to cryo in detail. I know you had a cryogenic training lecture last week from Addy. I'll touch upon some of the considerations that I've come across. You've already learned about fittings and had a session with Eric, so I'm not really going to go into any detail on fittings and propellant storage and handling either. So, like it says in that box, like these are meant to be, it doesn't include every single detail ever, but I've tried to get down as much as I could in the past week or so about my experience in designing feed systems here at LPL. Everything that I've learned basically in the past few years. And I was going through these slides and I don't think there was one thing that I knew before I got to LPL. So, like being able to, if you learn something today, like being able to give all this information to you, like for those of you who just joined, I think that, like, I can't wait to see basically what LPL produces in the next 2 years. Also just feel free to ask any questions throughout, even if it doesn't relate directly to what's on the slides, because you're in LPL, you've seen the feed systems. Yeah, just fire away and I'll do my best. So yeah, again on the scope, I think this is from modern engineering, but this is kind of like a diagram showing all of the kind of aspects of feed systems. Like I said, we're just going to cover pressurized feed systems, specifically direct gas pressurization. There's some other ones there. We're steering clear of the right-hand side of pumps and turbines and stuff. Specifically, we use this by stored inert gas instead of, sometimes you can vaporize the propellant, say if it's cryogenic, and feed that back to pressurize your tanks. As received instead of heated. Heated you see quite a lot in industry. We haven't touched that yet, but it might be something we'd like to explore. And then regulated pressure as opposed to blow down, which just means you don't have any pressure regulators. So that's kind of the path we're taking. There's a lot more to learn in the future, but that's for the future. So first off, really important, some good sources of knowledge and advice. The alumni, I'd like to point out, we have alumni in all, or have had experience in all of these companies. So if there's not a company there that you definitely really like to work for, then I don't know, come tell me. But basically all the big space companies, people have had experience with. I know David worked at Stealth, but they don't have a logo. Their website is just a black screen, so I didn't put it there. But also, so these are all LPL alumni, but also we've kind of been talking to one of the founders of Relativity who came from RPL, because LPL didn't exist when he was here. So, but definitely reach out to alumni. They're always really happy to help. Suppliers and manufacturers, get on the phone to companies like Swagelok, Omega, ask for an engineer. Like, I don't know how much great advice I've gotten from speaking to actual companies. You also get some crappy advice as well, but you just got to work with that. Some textbooks I'd recommend, definitely these three: Modern Engineering, which is the one on the right, Rocket Propulsion Elements, and Liquid Propulsion Design and Analysis. It's known as SPAD, if you guys have seen SMAD. It's kind of like, these three are like the Bibles for liquid propulsion. I believe if you work for SpaceX, you get given Modern Engineering on your first day, so it's legit. The NASA Technical Report Server is another great source of information, things like special publications, SPs, and that's just like hundreds and thousands of things that NASA have ever published. So it can be anything like old publications, like on this one on like lines and bellows and hoses, to like new stuff, research with like this lander, or, you know, it covers a massive range and it's used throughout industry. I don't know what our relationship with XQ is right now, but people from industry, like testing sites or other professionals, the A-Rocket email forum is, it's kind of it's a forum, but it's like an email list, and people like start threads and can ask questions. Or I've asked a few questions there in the past. So if you visit their website, you can like sign up. You might want to put it in a separate folder though, because it's a lot. And then Grumman's notes, obviously. So really quick, I just want to step through the history of LPL feed systems. This is before my time, but I'm sure the guys have explained like the history of LPL. But started off in 2015, and these are the first feed systems. So LPL didn't really have very much money at all. There's a shop called Norton Sales in Hollywood, and basically they just have loads of old space hardware, valves, hoses, like you name it, to like entire engines. The guys basically went there and strung together these feed systems pretty much with no hard line, just flex hoses like everywhere. There's like a regulator on the floor here and stuff. So it's nice to look back and see where we've come from. But I call these like the snakes, the NOx, the nitrous oxide engine, and blue steel snakes. And then just before my time in summer 2016, they kind of consolidated all that onto a wooden board, and that's what you see in the lab hung up. We like to look back on that. You'll also notice there's only 2 bottles there of gas. There's 1 oxygen as opposed to 8 we have now, and 1 nitrogen. And I'll touch on a little bit about some problems with this feed system later. And then we got to Hydra version 1. I don't have the date here, but this is in spring 2017. So this is what it looked like the initial time we thought we were done with it. It's really ugly, and there's wires everywhere, and it's a mess. We built it right where I'm stood here, in basically no space at all in the lab. This is basically where we built it, but it looks a lot different now. And the point is that you need to build feed systems with iteration in mind. We honestly didn't know what we were doing at this point, but then we had Hydra V2, the kind of intake when me and John did the big recruitment fall 2017. We were like Honza, Eric, Paul, we all built Hydra V2 and had the first successful firing of LPL, what we consider successful. So it's kind of a brief history. I think it's important to kind of show how the lab's progressed, because in the next 2 years it's going to be sick. Oh, and of course the water test stand, which was kind of a recent addition. You all know that. So another kind of preliminary thing, some useful design tools. RefProp is great. It's a great tool. There's an online version as well called CoolProp, and the NIST website also has like a great database. But we have RefProp on one of the lab computers, and it's just basically a big thermodynamic fluids like database. where you can plot like graphs and tables of like pretty much any thermodynamic property or relation you want to. So that's great. Learn how to use that. And that's a CEA. This isn't so much for feed systems, it's more combustion properties, so when you're designing an engine, but learn how to use that. That's a tool we use all the time. It's not for feed systems specifically, but a good knowledge of what is going on in the engine is going to help you, if you're on the feed system team or the testing team, it's going to help you diagnose like why the flow rate was like off or something. So that's another good one. And then also for suppliers and manufacturers, they have good tools online sometimes. So Swagelok have a reg simulator. Omega has these configurators to help you like pick out components and stuff. So sometimes I've like been trying to find components, and months later I've realized that website has a great tool in like the resources section or something to help you size stuff. So let's get into some of the theory. I'm not gonna, this isn't a fluid dynamics lecture at all. Ignore this is wrong. But I'm just going to point out a couple of aspects of gas and liquid flow that are important to consider when designing feed systems. So like I said, this isn't all the details, but it's just some things that I think are important. So choke flow, for those who are not familiar, the flow is said to be choked when, if you decrease the downstream pressure, there's no more increase in mass flow. So if you've got a valve and you have a certain flow through it and you decrease the downstream pressure, you've got more pressure drop, you've got more drive over the valve, you'd think the mass flow increases, but if it's choked, it does not. And the condition is when the flow velocity in that valve reaches the sonic velocity. Also, the condition is, you can find out if it's choked or not if the downstream pressure is below the critical pressure, and this is the equation for critical pressure. Usually it's about half the upstream pressure. So if you have any situation in your feed system and you know that the pressure upstream of a valve is more than twice downstream, so this is any time you're venting pretty much anything from a tank that's above 2 atmospheres, which is nearly all the time at LPL, this flow is going to be choked through that valve. So that's just something like interesting to consider. And then if the flow is choked through like a nozzle, then this is the equation that relates like your mass flow, your temperature, the nozzle area, and pressure. So
Mike, you're talking about when the gas escapes at the valve before the regulator?
Sorry, say that again?
This choking happens all the time, gas escapes container above 2 atmospheres. You're talking about the valve that's on top of the tank before the regulator?
So a valve, what I mean by valve is any kind of flow restriction. So
every
an
single
orifice,
valve in the feed system is choked?
No, because inside a feed system, if you're at 500 psi on the inlet and 450 on the outlet, the drop is only 50 psi. It doesn't drop to the critical pressure. If it's 500 psi on the inlet, which is P0, then this should be 0.5 P0. Note that down afterwards, wherever it is. Then the pressure would have to drop to 250 psi for it to be choked. So very rarely through a system do you drop that much in pressure over one valve, but on like the outlet, like a vent from like if I got the oxygen bottle, it's like 2,000 in there and opened it, it's going to atmosphere, it's more than a 50% drop, so it'll be choked. I just thought, note that down. That was wrong. 0.5. This should be all times by P0. Yeah. So it's the critical pressure over your inlet pressure is always around 0.5. So another aspect of feed system design is if you have a tank, like a gas supply tank, the oxygen tanks on Blue Steel on Hydra, or the pressure tank and it's depleting, like during a firing or whatever. The gas is, obviously the tank is going to be losing pressure, but it's also going to be dropping in temperature. For small systems, like systems with small flows and big supply tanks, it's not too much of an issue. You don't really see that much drop in temperature, but say for the QTech vehicle, and we're pulling out a large flow of helium there, the drop in pressure is significant over, say, a 20-second period, it's going to drop in temperature significantly, and that's going to affect the flow downstream. So I was actually speaking to that, yeah.
Are these graphs using the ref prop data, or is that ideal gas law?
So these graphs are using ideal gas law.
Okay.
Yeah. I literally added these two graphs before when I got to the lab, and it was fire alarm stopped ringing. But these graphs are just some like relations I plotted when doing the feed system sizing for the water test stand. And so this is just time plots of pressure and temperature for a maximum flow test of the water test stand, which we haven't done. You haven't even been near yet. But this is assuming isothermal expansion. No, sorry, isentropic expansion in the tank. So disregarding any heat flux in. So it's kind of a worst case estimate. Down here, so a lot of these slides, I will reference some good reading material on this. So down here is like some more theory about this. But what we've done in the past in LPL, like I say here, is we just wrote a simple MATLAB script to simulate that tank depletion. So you have a fixed mass flow coming out the tank, and every, I don't know, millisecond you take a little bit of mass flow, you see that pressure drop, what's the corresponding temperature drop, recalculate the mass, the conditions in the tank, and just iterate like that. And that's what produced these graphs on the right. I do have a graph of like if you just kept going and going for like 20 seconds or something, and it gets to an unrealistically low temperature, like 100 Kelvin or something. So this method is only really good for short, fast flows, so that you can ignore any heat flux back into the tank. Another thing about gas flow, which I actually didn't discover until kind of recently, is the Joule-Thomson effect. So there's a common misconception that when a gas is flowing through a valve, because of the pressure drop through that valve, you're going to get a corresponding temperature drop, maybe according to the ideal gas law or isentropic expansion or whatever, but it's actually defined by the Joule-Thomson effect, and it's similar, and for a lot of substances the temperature does drop when the pressure drops. But for instance, helium has, for most of its temperature range, we're never going to use helium at 50 Kelvin, so for most of its temperature range, helium has a negative Joule-Thomson coefficient, which means that actually when you force helium through a valve and the pressure drops, its temperature will actually rise. So I anticipate that when we use helium for the QTech vehicle, for instance, we're going to see that. But Joule-Thomson coefficients can be found for any substance on like the NIST website. So if you just go here, you can plot. This graph was actually made from the NIST website. So this is a dome regulator controlled by a pilot regulator, and this is the inlet here. You see it's not frozen, and then the entire thing is frozen. It's not cryo going through here because everything would then be frozen. This is literally the Joule-Thomson effect causing that temperature drop. I think that's a pretty extreme case because this seems to be like the poster picture of the Joule-Thomson effect. So just a couple of like aspects there about gas flow to consider. Now liquid flow, liquids do have kind of version of choking called cavitation, and that happens instead of the pressure drop reaching a critical point. That happens when the static pressure at the narrowest point of a valve, or if the static pressure as it passes through the valve drops below the liquid's vapor pressure, it will flash to a vapor, and because now you have a gas in the flow, that reduces your average density and kind of clamps the mass flow rate. You're not going to get any more mass flow through there, because any more pressure drop you try and put over a valve, you're just going to get more gas, more liquid flashing to a gas. So this is like a big problem in pump design, for instance. But we can use this to our advantage in feed systems to clamp the mass flow rate. So you can design these for a particular mass flow and a particular upstream pressure, such that if you meet the upstream pressure, then it doesn't matter what goes on downstream, you're not going to get any more mass flow through it. So I think the guys are thinking about these for the QTech feed system. We haven't used them yet, but like UCSD use them on their test stand. They're used like quite a lot. So I just
Is this?
Yeah.
So cavitation is actually used to clamp flow rates in industry. It's like used on purpose.
yeah.
Interesting. 'Cause it can,
I know it's used in rockets.
it can like destroy metal.
Yeah. So yeah, that's another
Erode
thing.
it.
If it's too violent and vigorous, then yeah. But if you size it so that you just get a few bubbles, you're kind of on the edge, then they are used like for that purpose. But that's interesting. Maybe it does still degrade it a little bit, and kind of got a limited lifespan for that reason. But I don't know. So water hammer. This is something we have seen at LPL quite a bit. And this occurs in liquids because they have high density, and so when they're flowing, they have high momentum. So if you have a high momentum flow and you suddenly close a valve, you're basically slamming that flow into a brick wall, and it can cause quite a severe pressure spike. And so either you design your system to be able to handle that pressure spike, or you can close the valve more slowly, or like some kind of commercial applications have one of these arresters, which is a small volume of gas which kind of acts as a shock absorber. So we've seen water hammer on Hydra, on the water test stand, and kind of the solution is to close the valves more slowly. Since we use pneumatic valves, we can control how fast or slow they actuate, and it solves the problem basically. But then you kind of it's a trade-off between that and how fast you want to stop the flow. Also, it's interesting that if the pressure spike is large enough, when the pressure wave slams into the end and goes backwards, you can actually vaporize. You drop this below its vapor pressure, and it flashes just like in cavitation.
I think one part that we saw it in was in the injector. So like when we opened the valve quickly, the injector experienced the water hammer.
Right.
So to oppose that, we opened the valve more slowly, and that eliminated that. So that's one instance where we could do that. But like closing the valve may be a safety issue.
Yeah.
You need to close the valve.
Yeah, that's true. So it wasn't actually a valve closing. It was kind of an effective valve closing when the flow is traveling from the valve on Hydra all the way to the injector. It has like no resistance, then it hits the injector, and it's a tiny little hole, and it's kind of like valve closing. So yeah, this is important. So how do you figure out how much mass flow rate of pressure you have? So if you are pressurizing a tank of liquid, and you know the liquid flow rate usually because it's what flow rate you want into your rocket engine, but what's the gas flow rate coming in? Mass flow rate is conserved throughout a system, but only throughout that one fluid. So everything downstream in the liquid line will have a conserved mass flow. But that's not the same mass flow as your pressurant, because that would be absurd. So one thing that you can relate the liquid flow and the gas flow is the volumetric flow rate at the interface between the two. So kind of by definition, or just trivially, the volumetric flow rate of the gas is equal to that of the liquid at the interface, because the interface moves, the interface is common to both fluids, so that's true. And then if you know the pressure in the tank and the temperature in the tank, then you know the mass flow rate of the gas at that point. And then that mass flow rate is conserved all the way up through your pressurant line. So this is kind of like step by step of how to calculate that. So it ends up being that the mass flow rate of the gas is the mass flow rate of the liquid times the density at the interface times the density divided by the density of the liquid. So pretty simple relation. So for example, I just did like an arbitrary flow rate for like Hydra, Blue Steel, or Jesse and James. 0.5 kilograms a second for kerosene, 1,000 psi pressure in the tank in 300 Kelvin turns out to only be like 5 grams, 50 grams a second for the nitrogen, so pretty small.
So Mike, when you guys were sizing Hydra, did you basically just assume like the maximum flow rate of fuel that you guys were aiming for, and then you just sized like the nitrogen bottle based on that?
And the initial lines on Hydra for the fuel were like all 1 inch, which was, we actually just picked that because the oxygen was 1 inch. It was kind of stupid, but they're now ½ inch. But yeah, basically you would just, what are your requirements? What's the maximum flow that you're wanting to transfer down the lines? That gives kind of your worst case or maximums for everything. And then from that mass flow of the gas, then you can basically do anything with the upstream line that you want. Like that's the same mass flow that's coming out of the bottles. So I've talked a lot about pressure drops through valves and stuff. And so here are the equations you need to calculate the pressure drop through a valve, or the mass flow rate through a valve given a certain pressure drop. And it boils down to the 2 coefficients, one called the flow coefficient, one called the discharge coefficient. And for so long, I was totally confused as to why there was 2 and what the differences were, probably for like a year, I don't know. But it just took a little bit of reading, I suppose. But they're very similar. And CV is actually just a more general kind of form of CD. So you notice that CV, Q is flow rate here. I should really point this out, but it's in the Swagelok valve sizing bulletin. Q is flow rate, mass flow rate, and this is the specific gravity, and this is pressure drop. There's no area here in the CV relation. There is an area here, and that's the flow area. But if you have a valve like this one, this is an omega cryo valve. If you have this valve, what is the flow area? Like the flow comes in here, it goes around these little like avenues through the poppet and out. There is no like defined flow area, and so that's why CV is used pretty much universally for valves. It's kind of like it's a flow resistance, but it's like the inverse of, say, a resistance in an electrical circuit. So a larger CV will result in a lower pressure drop or lower voltage drop. So that's why that's used for valves. CD, on the other hand, is used for, say, like a venturi or an orifice, or like the orifices on an injector pintle or face, because then you have a well-defined area. So you might ask, why not just use CV all the time? Why bother like defining the area? And the reason is CV. This is just the CV for this valve. Like, it doesn't matter. So it does matter how big it is. If you make the valve twice as big, you're gonna have a different CV. So for every valve size, you need to measure and quantify the CV. When you're designing an injector, you might say, okay, I just want a square-edged orifice, or I want a venturi with this kind of sweep to it, and that shape will have a CD associated with it. So it's the valve shape, not the shape and the size, that dictates the CD. So what you could do is you could say, okay, I want a square-edged orifice, that's a CD of 0.6, say. Then you could, but the flow is not big enough in our simulation. Okay, make the flow area a little bit bigger. It's going to have the same CD, so you can kind of predict how to kind of iterate on your area. So, So they're used. They can be used interchangeably. Like you can define a CV for an orifice, like we've been doing in our orifice testing. If you don't care about defining a CD and then changing the area or whatever, you can use CV. So I was going to include, maybe that's later. If it is later. So just like in electrical circuits, you're going to have more than one resistor, you're going to have more than one valve, or orifice or venturi or whatever in your system. And because CV is like an inverse resistance, they add up in series and parallel the opposite to resistors. So in series, your CV of these two together is this 1 over the CV of 1 over CV of 2, the opposite to resistors, and then if they're in parallel, you just sum them. And I've linked here the swage lock valve sizing technical bulletin. Everyone should read that if you haven't already. That basically has all the stuff I just talked about in there, and more. And also it references this, which is the ISO standard for valve sizing. Read them and you'll know it all. You'll know more than me, at least, because I haven't read this yet. I discovered it the other day.
Hey Mike.
Yeah.
So just a general question specifically for swage lock valves. I found that when they have their flow data for calculating the CV, they'll give you like 3 data points or whatever, and then if you like back calculate the CV from that, it's often like it varies quite a bit, like it goes from like 0.2 to like 0.5. So when you're acquiring your components, like how do you account for that?
Yeah. So I know exactly what you mean, and it'll give you like 10 psi drop or like 15 psi at like a tiny flow rate, and then you're like, but I'm supplying an engine with like a huge flow. Yeah, so that happens for check valves. Have you found that?
Yeah, I find
usually
for check valves and honestly like a lot of things on swage lock, they give you like the 3 data points at like 5, 10, and 15 psi pressure drop. And then you calculate 3 CVs, but they're all like kind of wildly different. Yeah, so for check valves, I'll get to a diagram on check valves, but I think that's pretty much because depending on the pressure drop, it opens a little bit more or less, and you have like a slightly different flow path as the valves, like the spring is retracting. Yeah, generally you just do your best with sizing that and kind of take a worst case and then just test it. I don't think so. That's for check valves. You kind of just need the pressure drop to be over the cracking pressure. I found it with filters too.
With filters, like, Are you kind of like on the borderline in terms of like pressure drop through the system? Because if you just kind of take a worst case, and then with a lot of this, like even the CV of valves, they've tested it, but you come to flow it, it's a different temperature, it's a different fluid, like this and that. It'll be different, but at least for like ground systems, just test it and see. Okay. And when you guys build like a flight system, maybe you're getting on the edge of like how much pressure you have in the tanks. And you're just gonna have to test it beforehand. So for like a ground system, basically just like acquire the component, and then when you're doing cold flows or whatever, you might have to make it like small adjustments to what you predicted. Yeah, I mean, just try and extrapolate. I called like swage lock and asked them to like give me more data, and they just don't. So it's a struggle. So this one, I tried to find this graph in the lab, couldn't do it. But there is a relation between CV and orifice area. So I said that CV doesn't have an area associated with it, but if you know your CD, you can like calculate the orifice area like required for a certain CV, and that's useful sometimes. But everything you need to know about that is in this link. I'm going to add the graph afterwards though. So that's valves. Now what about tubing? I'm going to cover valves and tubing. I'm not going to cover like losses in elbows and fittings and stuff. I might add that afterwards, but that's related. You can relate that to the losses in lengths of tubing. So what I've used throughout is the Darcy-Weisbach equation, which is there. And that relates, you can get like your pressure drop per meter or per foot or whatever from the density, the tube diameter, the velocity, and this friction factor. Now in the past you could use, or you can use a Moody diagram if you want to calculate your friction factor, which depends on Reynolds number and the roughness of the pipe, or the relative roughness. But I've been using this Churchill friction factor, which the guy made in 1977, so it's pretty old, but the internet, not Wikipedia, lists like 40 different relations for the friction factor, but it says the only one that works for any flow regime is this one. So I couldn't find a downside to using this one, and that's what we've used in sizing lines at LPL thus far. Interestingly, I actually found the other day that the Moody diagram is plus or minus 5% accurate. Not sure how accurate the Churchill relation is, but at least you can stick this relation in an Excel sheet or a MATLAB script instead of having to use the diagram every time. So this way of calculating this is just for incompressible flows, but you can use it for gases if it's and can consider it incompressible. So if the Mach number is below 0.3 is usually considered incompressible, and for our gas flows, saying like Hydra, we actually want to keep that oxygen below 30 meters per second. So that's way less than Mach 0.3. So we've been using this for gases as well. You can do that. And how we've used this, so this is a kind of spreadsheet that I made for, I think we made one for Hydra, but then I think this is for the water test stand. Just when you're kind of sizing the lines, this is useful, and I think we've probably adapted this for future feed systems as well. But you have like the tube diameter here, and all this stuff is the Darcy-Weisbach, and it gives you the pressure drop per meter in the lines. So see, if I made the water lines 1.5 inches in diameter, so this is for maximum flow. So you can set like the flow and the pressure and stuff up here. This is maximum ever flow. Could have had 1.5 psi per meter, really wanted, but I mean that's peanuts. And anything we're flowing below that, we're going to get even less, and we're going to have 1.5 inch lines. Like Hydra's biggest lines are 1 inch, and they're an absolute nightmare. So in the end, I settled for 3/4 of an inch, 70 psi per meter drop for maximum flow, but we are nowhere near flowing maximum through the water test stand yet. So it's kind of just like a trade-off between your pressure drop, like how much pressure your system can produce at the maximum flow and the maximum like pressures, and the whole workability, finding components, fittings that don't leak, bending tubing. We've bent a lot of the 3/4 inch lines on the water test stand, but would not have been able to do that easily with 1.5 inch maybe, but the bend radius would be this big. So this is just a big trade-off. And then you can see down here, so I should point out that these blocks, this block is the water 1 line, then we have the water 2 line, 2 lines of water lines on the water test stand, then the nitrogen 0 line, which is like the supply when it's in one tube. I mean, branches, you could do one of these blocks for every branch of a feed system, but in the end, it's too much. But it does split into the nitrogen 1 and nitrogen 2 lines as it pressurizes each tank, and they're pretty long lines. So judging by these pressure drops, you can kind of get a feel for what size lines you need in other like subsidiary lines. So I'll have the P&IDs in a minute, I can kind of go into that. But this table, there was a little bit of confusion about this initially, but this table uses that relation between the gas flow in to a tank and the liquid flow out. So that's why you see the tank pressure of the liquid in here. You need that because that's going to affect the flow of the mass flow of nitrogen in here. So that's on the drive. Ask the guys about that if you want to use it. So another thing, how constant is the discharge coefficient? So it kind of applies to the flow coefficient as well. They're both meant to be constants. A particular valve has a particular coefficient, but it's not entirely true. It does vary with Reynolds number, and so it's kind of hard to find info on this, but this is a paper, I've linked it here if you're interested. It's a paper where some people measured the flow coefficient, the discharge coefficient of particular restrictions. So there's venturi, an orifice, a V-cone, whatever that is, and a wedge. And you see that they deviate hugely in kind of the laminar flow regime and kind of the transition regime here. But I've done some calculations of some typical flows at LPL, and they're all turbulent. So we're looking good. Like they kind of end here, and this here is the discharge coefficient correction factor. So it's how off the discharge coefficient will be from, I'm assuming actually from a completely turbulent like measurement. So there was some kind of confusion about why we were getting weird data when we've been doing these flow tests compared to what's quoted. So I don't know, I can't help with that, because this makes it seem like our flows are all turbulent and we should be getting pretty accurate results, but should look into that a little bit more. So another thing that you'll see a lot is standard volumetric flow rate. So nearly all flow curves for regulators, valves, whatever, they're nearly all quoted in SCFM, which is standard cubic feet per minute. Funny story, we didn't know what this was when we bought the first valves at LPL. We thought it was just cubic feet per minute, but we were running at like 1,000 psi, and so you're pretty much a factor of like 550 like off. So we bought some valves that don't work, basically, or regulators. That was it. We thought the nitrogen regulator on hydro would be able to do the oxygen flow. Nah. So that was a waste of like $1,500, but I think Atticus is going to use it now, so it's not a waste. But anyway, what is it? So standard cubic feet per minute, or standard volumetric flow rate, is just the normal flow rate weighted by the ratio of whatever pressure your system is running at divided by atmospheric pressure, like standard pressure, and then multiplied by the ratio of standard temperature over temperature in your flow. So that's SCFM, which is people call it. And so I like to work in like SCFM, PSI, and kilograms a second, which is weird, but I think so what I'm doing is I'm relating the SCFM here to a mass flow rate in kilograms a second. So you get this constant here because of the cubic feet per minute part, and then if you turn your volumetric flow rate into a mass flow rate over density, this density becomes, assuming ideal gas law, P over RT, and then the P's and the T's actually cancel out, and you end up with this constant times mass flow rate times this density. This is a new density here. It uses the same R, but it's actually standard density of your fluid. So the density of your fluid at atmospheric conditions, which is a constant. So my point is that SCFM turns out to be, it's this constant. SCFM is a constant times mass flow rate. So contrary to popular belief, it's not really a volumetric flow rate. It's actually a mass flow rate just multiplied by a constant. And so when you're reading the graphs, you got to think of it in terms of the fact that it's behaving like a mass flow rate. So that's my point. But that's the equation for standard cubic feet per minute. And then,
do you know why this is what everybody uses? And why?
Anyone? No.
Just is.
So like next slide, like on this graph here, it's standard feet cube per minute. I don't know why. Trying to wrap my head around it. Maybe I'm missing a point, but I always like to think of it as if it's like a mass flow. But yeah. So a lot of, this is kind of an aside, but a lot of graphs you see, so this one I'm going to talk about next is for airflow, and the regulator curves you'll get are probably for nitrogen flow or airflow or whatever, but you're not going to be flowing air most of the time. You might be flowing helium, and so you can read these graphs, but it's going to be slightly different, and the factor by which you have to correct your values is, it turns out there's the ratio of, the square root of the ratio of the specific gravities. So this is all in the swage lock valve sizing technical bulletin. But some of these, some specific gravities, so air is 1 by definition, oxygen is just over 1, nitrogen is just under 1, but then helium is way under 1. So if you read this graph, for instance, but you're actually going to be flowing helium through this valve, it's going to be quite a long way off, but you can then correct for that. So yeah, these are straight from the technical bulletin. I put some example calculations here because I'll just go through one. So I've used these graphs like all the time when like procuring components. For instance, you're online, it's like, oh, that's a CV of this, what's that pressure drop going to be? Just kind of quickly like go over the graph. or if you're trying to troubleshoot something really quick, like these graphs are really, really useful. Get used to reading them. So, what do I say? What valve CV is required to keep the pressure loss below 50 psi if the inlet pressure is 800 psi and the flow rate is 500 standard feet cubed per minute? Okay, so you might immediately ask here, okay, I've specified every single thing on the graph. So the pressure loss 50 psi is like here. The inlet pressure is 800 here. 50 psi loss here. Okay, I go down. That's like 200, say 200, but I've specified 800. So this graph is for a CV of 1, and so I will need a CV of 4. Oh wait, have I just messed that up?
You wanted 500.
Yeah. Sorry, oh yeah, 500, not 800, that was the inlet pressure. Sorry, 500 scuffum. So I got 200 scuffum, need to multiply that by 2.5 to get the 500 scuffum. So you basically multiply the flow rate by whatever CV that you have to get what flow rate will be through your valve with that CV. So just something, a little trick to these graphs, and then you can kind of do the same in reverse, which I do here. So all in that technical bulletin, read it because it's really useful. Okay, so now I'm moving on to kind of approaching feed system design section. It's more like qualitative. So some considerations which I think are important, which I kind of started with when designing the water test stand, for instance. So flow rates and duration requirements. Now what flow rate do we need, and what how long is it going to be flowing for at once? Obviously that's going to affect your propellant and pressure and tank sizes, and also the flow rate will affect the general size of the lines, components, and sensors. So I would probably do that first. Get how big this whole thing is going to be. Then what operating pressures are we talking about? This is going to govern what everything's rated to, for starters, and also what materials you might want to use in different cases. Then what working fluid are we dealing with? Also, this determines materials even for benign liquids like water, for instance. Like that pump in the water tank is rusty as hell, so probably a bad choice there. But then other more significant effects like oxygen, you don't want to use certain materials in your oxygen lines. Now I'm not really going to go into that, but different materials have different temperatures. What are they called? Ignition temperatures. And if you have a high pressure ox line that's flowing really fast and you have any debris in there and it hits like a soft material, maybe like a hydrocarbon, if it's like a rubbery seal or something, it can ignite it, and that can start a chain reaction and end up igniting your steel tubing. We've never had that happen, luckily, but because we've chosen the right materials. And then operation, I just slapped this one in, is it human or computer controlled? That's going to affect safety measures and all sorts, like if you've got a front panel or whatever. But then, how do you go about starting this? Sometimes there's more than one solution. So have you got any constraints? So an example would be the QTech propellant tank pressures, or rated pressures for those tanks. Really annoying constraint that really restricts what we can do in the lines there. They're rated like 500 and 600 psi, and so between those tanks and the engine or the atmosphere, we have to have the engine for starters, the chamber pressure, and then we've got to have all those pressure drops through valves upstream of that, and so that's like a trade-off with the engine sizing as well. And then maybe not have a weight constraint on the QTech vehicle lab space. One of the reasons why the water test stand is so tall is because we still don't have that much lab space, but we really didn't at the time, and I just was trying to keep it compact. Also, draining downwards is also a benefit, but then also cost and time, obviously. And then what are the objectives of your feed system? So for the water test stand, the objective was to enable water flow testing of any current LPL engine or component. So I'll get into kind of requirements on the next slide. But that was what it was supposed to do. Hydra, on the other hand, was literally we just wanted to build a mobile test stand. We just wanted to build a feed system. We didn't really think too hard or too far ahead into like, oh, what Jesse and James or what's Valerian gonna need? Like, we weren't thinking it was gonna be able to take that much thrust. It was pretty much for Blue Steel 1.0, and so maybe some problems now with iterating on Hydra, and it's kind of awkward to fix and change things, but that was because that was the purpose. So requirements for the water flow test stand. This is just for my CDR. I'm not going to go through all of them, but it's really important if you start a feed system to list down all of what I would call like primary requirements. Like the feed system has to do this, otherwise it either won't serve its purpose, or like you really wanted to do this, you know. So for instance, the first one, flow water through components and engine assemblies, obviously. Then there's a mass flow rate requirement here. So I required it to flow at 5 kilograms per second total, or 3.5 kilograms per second each line. Where do I get those numbers from? Well, what is the flow rates through the engine or the components that we need? So Valerian's a big guy, like not really going to make an engine bigger than that anytime soon. I don't know, but that's got a flow rate of like 4 and a bit kilograms per second. But then kind of like each line, what's like the range of OFs that we're going to test? Probably not going to use hydrogen anytime soon, so we're not going to need an OF of 6. We might need an OF of like 3 or 4, for instance, if we want to do methane. So that's kind of where those requirements came from. So it can basically supply any test of any engine we're going to do. Then what kind of pressures do we want? So that's like, okay, if we're testing the Valerian Pintle, it's like 70 psi drop. That's tiny. But what if we're doing like a future engine, the chamber pressure is 2,000, the pressure drop over the injector is like 30% or something high, and we've also got the regen system on there as well. It's another 150 psi. Like it racks up and up and up, and it got to around 800 or 900 psi, like worst case. So the regs can do 0 to 900 psi. So it's kind of like, yeah.
Just like one thought, like for example, like the functional requirements, the second one.
Mm-hmm.
How do we know it's able to supply 5 GeV?
We don't. Yeah. So that was something that I wanted to do. Didn't have time, and I would suggest doing that in future, because that would be sick to try and get 5 kilograms out of that. But yeah, I wanted to do all these tests, like proof test up to like max pressure, which it hasn't been yet. Flow to the maximum flow, that will be sick. But never did that. The biggest flow we've done is basically through the James injector. So this is what it was designed to, but it hasn't been put through its paces yet. So, and then some of these other ones, maybe I wouldn't say are primary. It's like, this is like run 10 maximum flow tests before replacing pressure in cylinders. That's kind of like a convenience thing. Not sure if it can do that, but it was designed to do that. So point is, get all these requirements down before you start making a schematic. So schematics. You're probably all familiar with the what time are we on? Yeah. Probably all familiar with the P&IDs or schematics for maybe not all flow test stand, but at least for Hydra. We were calling them P&IDs for a while, and then X Quadrant said, don't do that, call them schematics, because it's not like 100% official. We've tried to make all these symbols like standard symbols. It's hard, there seems to be different standards. One thing that I would say is not good about these schematics are like the labeling of the valves. Well, they are good for us, we know what they mean, they're simple, but it might not be what industry does. So I call them schematics. So I'm probably not going to step through this, but I might refer back to it later. Then I just stuck a few points here. So the difference between moving from a schematic to a physical system. A schematic should only be an indication of the relative position of components. So like this needle valve is not horizontal, and it's it's actually right next to like these, and this gauge is on the same elbow as this, for instance. So this just gives like the relative, an indication of the relative position, but it should just be laid out to be easy to read, pretty much. Physical system is three-dimensional, obviously, so you're going to have kind of considerations like where does the propellant or the water flow under gravity? Maybe you want it to flow in a certain direction. Maybe for priming a system, you're going to want it to drain a certain way, or if something's evaporating, like cryogenic boil-off, you're going to want it to route in a certain way. So kind of obvious things, but kind of important to get in your head when you're moving from a schematic to actually procuring components. I would say though, something I didn't do for a while, actually on the water test stand, is I'd have like a crappy schematic, and then I'd be trying to find these components, and then I'd be like, oh shit, no, I need to change this, and I'd literally change this. This isn't the second version, this is like, it went to like 1.9 and 1.13, and I just decided to make it 2 or something. But one of my number one rules is get your P&ID or schematic like down. Make sure it is exactly how you want it to be, and you've thought through every eventuality really before you dive too deep in component selection. Then maybe you want to start procuring components because you don't even know that you can get a particular component that size. So the electronic reg here, like maybe those didn't even exist for this flow. So you're going to want to look into some of the critical key components, but I would definitely say get your P&ID, like get it reviewed by people before you really move on too far, especially with the CAD. That was another thing. I was like changing the P&ID, and then I had a CAD of the whole system, and like having to re-change that is a nightmare. So I just kind of stuck these 2 schematics here, which I might refer back to. So another thing to consider, should we take a 5-minute break? Let's take like a 5-minute break, unless anyone wants to carry on desperately. But it's at 4 p.m. so yeah, I'm probably about halfway through. So I know most of you guys have propulsion today, yeah, with Grumman. So yeah, I'll finish like well before then. So continuing with the kind of approaching feed system design part. So it's important to remember that feed systems are coupled systems. So specifically one line, what happens in one line will affect the other line, especially, well, if it's attached to an engine like on Hydra. The water test stand, the only thing that's really connecting the lines is the common supply, but this is a P&ID from some missile somewhere. But for instance, like for example, if this filter here, if the CD decreased, so if the filter like got blocked or something and the CV decreased, that's going to decrease the flow in this monomethyl hydrazine line. That's going to affect the OF, it's going to affect the flow rate into the engine. Now the engine chamber pressure is going to drop if we don't have a control system on here, like on Hydra. The chamber pressure is going to drop, and that's going to actually suck in, that's going to increase the total pressure drop between the chamber and the pressurant, and that's actually going to increase the flow of the nitrogen tetroxide line. So that's important because we see this kind of effect a lot, all the time in the feed systems we build. If we have some active components here, like a control system, like flow meter fed back to an electronic regulator, which could kind of adapt to this, and yeah, you could have that. But all the feed systems we've designed so far don't have any of this sophisticated control. And so that's what I mean by passive feed system. If it's passive, then it's going to be coupled in this way. Well, it will anyway, but you won't be able to control it. And we've seen this. None of you will remember. Wait, maybe did it go in Who was here? Atticus will remember, yeah. So we saw this with the blue steel 1.0 firings and the wooden fluids deck, right? So if you remember what that deck looks like, the lines were actually designed to be 1 inch. Somewhere along the line, the guys who made them 0.4 inches instead. No idea why. But what this led to, you'd think, okay, the lines are both smaller, we're going to have more flow resistance, the flow rates of both propellants will decrease. But that's actually not what happened. What happened was the flow rate of the fuel decreased, but the flow rate of the oxygen, decreased. So here we see the 1 inch line. This is a simulation from someone, I'll explain in a minute, but you see here the 1 inch lines at 1,400 psi reg pressure gave 0.938 of the ox, but when the lines were reduced, it gave 0.705. Okay, the flow rate's reduced. Yeah, the fuel flow rate actually increased, and this is that coupled effect coming into play, and the fact that an oxygen is a gas and the fuel is a liquid, which swings it as well. And that led to a low OF ratio and this wonderful flamethrower. These are multiple days. This happened over and over again, and it was pretty much just that the feed system was designed badly. So it's an example of that coupled system effect. Another thing, just a few tips here, anticipate iteration. We didn't really design Hydra to be iterated. It has been iterated, and it's simulated through the flow starting, the engine firing, it ramping up to pressure, and it just simulated the flow all the way through. So that's one method or approach to doing it, but it hasn't really been kept up. Hanmo, those of you who remember Hanmo, he took over the code and adapted it a bit, but it's kind of quite hard to use and understand. So it does exist, and it's quite good, sophisticated, but it has its little knacks. But you could press go. This is how I actually originally sized the blue steel 2.0 injector, using this code, basically just playing around with numbers, pressing go, and getting orifice sizes out. So it does exist if you're interested in reigniting that. So yeah, I was talking about anticipating iteration in designs. Also, if there's a small system that you're not quite sure if it'll work or not, don't just go ahead and order all your components, which we did for Hydra. You won't be surprised to believe. Hydra V1, we designed it and ordered everything, and then we got the reg and it didn't work. We got the solenoid valves and they didn't work. So don't do that. So for the water test stands, I wasn't sure. So this pneumatic ball valve here is actually, instead of being controlled via the LabVIEW and an electrical signal, it's controlled by a 4-way ball valve, a hand-operated ball valve from the control panel. I just wasn't 100% sure that this was going to work, so ordered these two things, hooked them up, tested it, it worked, and then kind of moved on. So just a little tip. Yeah, so another thing I could think of, what the guys I think have been doing, the YS13 ground support equipment. There was a lot of shall we use a pump or a boost pump, or shall we use high pressure bottles? Probably should test either or, maybe rent the pump or something and test out that before basing the whole ground support equipment on one methodology or the other. So this is a slide I didn't really have time to finish, but a really important consideration is power loss. What happens if the power goes in your system? So where are we? The power is lost on, actually this is better because it has more of it. The power is lost on Hydra. What happens to the valves? You're probably going to want your propellants to shut off. So we've made these valves normally closed. You want the pressure in this tank to vent, so that's why this valve is normally open. So considerations like that. And also actually specific to the water test stand, what happens to the electronic regs when the power is off? This is something that kind of confused me for a while until I got to the bottom of it. The regs don't close when the power is shut off. They actually remain at their current set pressure. So that's one consideration that I kind of had to take into account when designing that. But at the end of the day, the water test stand, it doesn't have any like propellant in it, and it's designed to be safe to use in the lab. So actually, if this system is under pressure, it's not like 100% safe, but it's meant to be safe to be around. You can't leave it overnight. That wouldn't be a good idea. But the fact that if we lose power and I have no vents on this, I didn't see that as a problem, because you can manually vent if you want to, because it's meant to be safe under pressure. But these two main isolation valves will close, for example. Okay. I'm going to skip over this because I'm a bit behind. So into kind of like the components now. So pressure regulators. There's a lot of weird and wonderful things about regs. You're meant to set it and it holds the pressure at a set point no matter what the flow. That's an ideal reg. Doesn't happen in reality, and this is something that we scratched our heads about when the regs weren't doing what we wanted on Hydra. The blue steel wooden board thing, like no one knew about any of the realistic reg effects there. It was just like, oh, that's a reg that we found on the floor in Norton Sales. Stick it on and it'll be that pressure, but it's not the case. So in addition to the lines being too small on that, the regs, chances are, couldn't supply the flow, and you just weren't getting the flow like anything out of that thing. So I've linked all good stuff here. It's pretty much it is all Swagelok. They have really good tutorials on reg sizing, how to read flow curves, etc. This one actually has more stuff about the Joule Thomson effect. Here's some nice looking regs down here. So, what do I say up there? Yeah, they attempt to control pressure and not flow. It's important. Sometimes people think that if you set the reg to something, you're going to get a certain flow. Well, it's going to try and give you a certain pressure, but the flow is all dependent on the flow curve, which I'll come to right now. Just want to mention there's different reg architectures, so this is probably not a full list. It's only 4, but this is like what's used on the water test stand, electronically piloted, dome-loaded reg. This is a dual stage regulator. I'll explain why you want to use them in a minute. This is just a standard manual reg, and then this is a dome-loaded spring bias reg, which I actually just learned about. I think it's dome-loaded, but you can bias the loading with an adjustable screw here. So I don't really know too much about them, but this is an example of a flow curve for a reg. So a regulator will come with an advertised CV, but that is the CV, like I say up here, that's just when the reg is fully open. The regulator is fully open, that is the CV, so that's what flow you'll get through given a certain pressure drop. But regs don't quite work like that. You need to look at flow curves when you're picking a reg. So a couple of important features is this seat load drop, or sometimes called lockup. Before a reg, sometimes it's way more severe than this. I should point out that this axis is your standard feet cube per minute, kind of just like your mass flow axis, and then this is your outlet pressure. So if you set the regulator at 75 here when there's no flow, so you set that, and then you're going to open your valve, and a certain flow is going to start going through your reg. The outlet pressure is actually going to drop. So this is really important for designing feed systems and picking a regulator. The first little drop, the seat load drop or lockup, is as soon as any flow basically comes out the reg, it's going to drop to this point. It kind of curves here, but most regs, it will literally just drop, which is why it's called seat load drop or lockup. It's like, as soon as the flow is getting smaller and smaller and smaller, as soon as it stops, it locks right up and it will increase that distance in pressure, or vice versa when it starts flowing. The region you'll be in most of the time for your flow is the droop region. So this is just a steady decrease in outlet pressure as your flow through the reg increases. So we want to be here. This is where we want our flow to be all the time. As soon as it gets past this flow, like 140 in this case, it starts rapidly dropping off, and that's actually when the flow is becoming choked through the reg. Has a little arrow CV there. I think you probably calculate the CV via this point. So an example of a flow curve. This is the reg for the water flow test stand. This is a random red line. Doesn't mean anything, but it's just to indicate. So I just do step by step here, like how you read this graph. So firstly, I should point out that these lines, you could be in the middle of these lines, and good luck to you. It's a struggle, but say, luckily, we are regging to 800 psi when it's static, and we have an inlet of 2000 psi. We're going to follow this line down. So if our flow is going to be 1/400, we're actually going to get less. We're going to get like 500 psi out. So that's a significant difference. It's like 800, 500 psi. That can ruin your test, your feed system. So really, really important to watch out for this. Again, you need to correct this if it's not air, which, yeah, this is air. If it's nitrogen or if it's oxygen, use that correction factor from before. If it's in the middle, do your best to kind of interpolate. I actually asked Testcom to give curves at a closer pressure to what I wanted, and they did. They were a bit confusing though. It didn't look quite like this, but you can always ask manufacturers. Like worst cases, they say no. So, what I didn't point out is one of the effects of regs is supply pressure effect. So what that is as your supply pressure decreases, that actually affects the outlet pressure as well, which is kind of indicated on these curves. Different supply pressures or inlet pressures will give you a different curve. But usually the supply pressure effect for a reg is negative or positive, but usually the relation is that as the supply pressure depletes, the reg outlet pressure actually increases, which is counterintuitive to me. One thing, if that's really an issue, then you can use a dual stage reg. This supply pressure effect is usually like 1 or 2%. So every 100 psi the inlet decreases, the outlet goes up by 1 psi. It's a small effect, but if it's really bad for you, a dual stage reg will exponentially decrease this supply pressure effect as it goes through one reg and then through the next reg. Let's move on. So, electro-pneumatic regs. So I chose to use these on the water test stand. Firstly, to get rid of all of these effects. The reg has the effect, but the control system counteracts the effects of droop, lockup, supply pressure effect. That was to get nice accurate control of pressure. It's also a convenience thing. Like you go to that water test stand, you type in a number and it regs there. You new guys may not have used the manual regs on Hydra yet, but if you have, you'll realize that they're an absolute bitch to control and hold steady, even statically. So, I mean, these are expensive, but I think it's worth it. So for those who aren't familiar, this is a dome regulator. So it's a normal regulator down here, but instead of twisting a knob to control it and push a spring in and out, then you use a pressurized gas, usually like shop air pressure around 100 psi, 110 in this case, and that forces this dome up and down, which controls the reg. And in this case, for an electronic regulator, or an electronically piloted regulator, the dome pressure is controlled by this device up here, the controller. And that controls this pressure by making these two valves, the inlet and the exhaust, they flutter and they open and close in such a way that it controls the pressure in here. And then they can use feedback either internally, externally from a sensor downstream. So we use a sensor like actually at the injector we're testing, either inside the injector, just upstream of the injector. So if we want to test at that pressure, we get that pressure. So that's external feedback or cascaded feedback. So I won't read this, but it's kind of a reference. Internal feedback basically it controls the pressure in the dome, which is fine. You can kind of you can control pressure in the dome pretty well, and you can snap to different pressures, that's fine, but really doesn't relate that well to the outlet pressure of the reg due to all these different effects, and it's not proportional. External feedback is great, right? You're taking the feedback from a PT, you can try and control that, but if that's way downstream, if it's not enough pressure at your PT, the reg increases, it takes time for that flow to go down and then to feedback. It can't really do it fast enough, and that's where you want to use cascaded feedback, and that's what we use on the water test stand. So if you're interested in this stuff, like, this is for reference. And that basically is the best of both worlds. This is the control system for that. It basically controls the internal dome pressure of the reg precisely, but uses the feedback, the external feedback, to kind of update its best guess of what the dome pressure should be for your set point. So that's that. And here are some examples. So this is, if you don't use, this is just internal feedback. So this is the set point going up in the green. This is what pressure I want the reg to be at. Pressure on this axis. This is the pressure that's actually down at the sensor. So it actually takes quite a bit of pressure here to even open the reg. I should actually point out there should be another pressure axis for this, because it's 0 to 900 on the outlet, it's 0 to 100 in the dome. But you see it's not really following very well. And then when this black line here is when the valve is opened, the water flow starts, and we get a huge droop. The set point is chilling up here, the huge droop when the flow starts, and that's exactly what we want to counteract with these electronic regs. And so I think the next slide, this picture up here is the regs we have on the water test stand, and it's like an integrated version of that, this that you see here. It's quite a nice little package. This test is when we use cascaded feedback. So you see the pressure actually follows the set point like almost perfectly all the way up. This is data from a test. So the pressure in the orange, the outlet pressure, is following the set point pretty well. We open a valve, and then this is actually an example of where I changed the feedback from in the tank on the water test stand to right at the PT. And you see it approaches it, and then it holds it nice and steady on the set point for the whole time. So that's why we use electronic regs. It counteracts these realistic effects. And then this one is for David. David was saying that you were doing a test of an orifice test of something, and you were getting results like this. Oh, where's my mouse gone? Results like this, like waves up and down, and that is either due to the controller tuning on the regulator, or it's because, let me go back to this really quick. Okay. Or it's because the flow is too small. So when you're sizing a regulator, imagine the curve. You're sizing a regulator, you want to know that your reg is not going to drop off the end before your flow rate. Yeah, you want the flow rate to be in the middle of that graph. But what I kind of overlooked is, okay, this system can handle huge flow rates, but can it handle tiny flow rates? The answer was no originally. We were testing the James injector down here, and we were getting this waviness. The reg was opening, the pressure, the flow was rushing in, the pressure jumped up, and then the reg was like, crap, I gotta close, and it closed, and it kept going up and down. And because it's a PID controlled, you might think, oh, the tuning is just bad. And it was bad originally, and then we worked at it, and we just couldn't. We tried to make the controller so slow, like lethargic, and we tried everything to make it creep up, and as soon as it cracked open, the pressure would just ram in, and you would just get this oscillation. And I realized it's because these regs are big, and they can't control very small flows. they're in that lockup region. That's the issue. And so I added in these just needle valves. You'll see them on the water test stand. They're like gold needle valves on the back, on the vertical lines, and those basically just restrict the flow and they make the regulator have to work harder and open more to get the flow through. And so it's kind of just like reducing the size of the regs. And so I've set them for the James injector, but now you're doing smaller flows, you're going to need to close them off a little bit more. So that is that. So yeah, these graphs, like on these two slides, are from the paper, and I just show how this is a fully open needle valve, then this is closed a bit more, and then closed a little bit more, and you get a nice flat curve here. So that's what we wanted, that holding that pressure nice and constant throughout the whole test.
So did you just do multiple tests to decide how
just closed it a bit more and until it stopped, and then maybe closed it a little bit more. You'll notice that blue line is not quite at the set point. That's because it's trying to make the orange line at the set point, which is the pressure out downstream of the reg. You can flick a switch and it flicks to the feedback mode. If you're interested in that, then I can show you after. I'm conscious of the time. Oh crap. Yeah, alright. I'm on slide 46 out of 80, so this is a lot of this is just for reference though. So sizing relief valves, FlowSafe here has a great guide, and that's where like these are from. If you want to size a relief valve, just read that guide, and you will be able to size relief valves. Thing about a relief valve, just looking at this diagram down here, there's a little electrical analogy here. If you have a supply of voltage or pressure, it's going through some resistive components, and then you have, say, a relief valve here, which is a resistance to ground, to the atmosphere. But then you also have your main flow path, which is your downstream components to ground, through the engine maybe, or through the component to the atmosphere. My point is that the relief valve has to be able to supply a certain flow out. If you can't, whilst remaining this set pressure here, you don't want the pressure in the line to be above the set pressure. So if you use an electrical analogy, the voltage at this point is the supply voltage or pressure weighted by the resistances of this circuit and this circuit. Kind of just boils down to the fact that the lower the set pressure, the bigger the flow the relief valve has to be able to take, which is to say that the lower the relief valve resistance has to be. So if you lower this, you're going to have to lower, if you lower that, you're going to have to lower the relief valve resistance to get the required flow. So again, using those relations from before, you're going to, I needed to say that we use a MATLAB code that uses all these relations, and it takes in the set pressure, the fluid properties, and it takes in the flow that it needs to relieve. And how do you work out that flow? So that's the flow that the relief valve will have to relieve if this valve is closed, is any flow that comes from the supply through the reg, say a broken reg, or someone's regged all the way up, through these components, through the reg, and out the relief valve. Now what's the pressure drop between the tanks and the relief valve? Well, the upstream pressure is the tank pressure, downstream pressure is the set pressure, and using the resistances or the CVs of all your components here, you can calculate the Q or the flow rate that you have to relieve using the CV relation. And what is the CV of the upstream components, like aggregated? Use those relations from before, and it turns out to be that. It's just for reference for relief valve sizing there. These are some graphs I plotted showing what I just talked about. So this is relief valve orifice diameter, like what diameter of that orifice you need to relieve the flow that you are required to, related to set pressure. So as we increase the set pressure, you don't need as much orifice area for a given flow. This is for a given flow. And then this is the relation between, again, the diameter and the regulator CV. So as we increase that CV, the potential for flow to come through and have to be relieved gets more and more, and so your diameter has to increase. So there's a function on the drive for like regulator size, relief valve sizing, and like to plot these graphs and stuff. I think it's in resources, design tools like MATLAB. If you haven't like wandered around the drive, just do so. You might find something interesting. I like doing this presentation. I found a lot of interesting stuff which I didn't know existed. I'd forgotten about. So yeah, it's a maze. Rupture discs or burst discs are sized pretty much identically. This is a good sizing guide for them. They use slightly different conventions, but rupture discs, relief valves basically just, when they hit the set pressure, they open to relieve that pressure. It's a safety device. Rupture discs literally break, and so you have to replace the disc each time, and you can't stop it. So this is really like a last resort device. So a good idea is to have a relief valve, and then if it really gets high in pressure, then have a rupture disc set higher, so like a last resort. Solenoid valves, not really going to explain like what they are, but kind of a top tip on solenoid valves is check the spec sheet. This is one of the things we bought for Hydra that they're just sitting in a drawer now. There's like 4 of them, and they were very expensive. And these are ASCO valves. We basically use these all throughout the Hydra feed system before we got the pneumatic ones. But we didn't notice, or we did, and we thought it was fine. Maybe we were just dumb, but this required pressure differential. So if you see that, that means this valve needs 145 psi difference between the inlet and the outlet to function correctly. That might mean to close correctly. In this particular case, this is the valve not powered, it's normally closed. This is closed and it's leaking out, and this was attached to the hose outside the lab, so it's really crap. But that's because we weren't having this pressure differential across. This valve is actually meant in like a gas pump or something for like your car. It's always trying to force like the gas out or something. So it's always going to have this back pressure. But if we're like filling up Hydra, filling the tank, and it's kind of running down to the ISO valve and it's kind of stopping there, there's no back pressure. It's just going to dribble out. And so watch out for that. There'll be a maximum as well, maximum operating differential, and you just can't go above that. So if it's an ISO valve, that's pretty much the upstream pressure that you can't go above. So I mean that's chilling. That's 5,000 psi, but this really is where we tripped up. So skip that slide. Pneumatics, for reference, like pneumatic valves. This is how the actuators work. This is how the solenoid valve, which controls the airflow, works. You can read that later if you're interested. So one thing that you'll see on Hydra and on the water test stand is this use of a buffer tank. It's actually really important because, so initially we got these pneumatic valves, right? And where is it? Like this guy. We hooked it up to the compressor that we have, hooked it in, tried to actuate it, and it went really slow. And I was like, the guy on the phone said this was going to open in 0.5 seconds, and it opened in like 5 seconds. So like really slow, so I was pissed. But then we kind of realized the outlet of that compressor has a tiny little regulator on it, and it just can't supply the flow to the valves. Pneumatic valves take a short burst of flow, but it's quite a high flow, and they give you the volume that they suck like through, and if you figure out the time, then you've got a flow rate, and your system to supply the pneumatics needs to be able to take that flow rate, and so that's your regulator here. So this is tapped off the pressure in line on the water flow test stand. Got a regulator, an orifice which I'll get into, and then pretty much your buffer tank, and then the valves. So, okay, we want a regulator which can take that huge flow. What if we open all four valves on the water flow test stand at once? Like a huge flow coming through, okay, get a big reg. Now we've got a big reg, now we're going to need a big relief valve. And what's the set pressure of this system? Like 100 psi. What's the inlet pressure? Like 2000 psi. From those graphs, the relief valve diameter that you need goes way up. And this relief valve, I like sized the relief valve, and it was like this big. It was like $2,000 from FlowSafe, and I was like, nah, well, obviously we're not getting that. And so it turned out to be one of the tiny little ones from Swagelock. The reason is you don't need a big regulator if you have a buffer tank, because the buffer tank acts like a reservoir that the valves can suck from, and if it's big enough, then the valves are firing off, and each one is sucking a little bit out, but they're not firing constantly. So you fire one valve, it sucks a bit out the reservoir. The reservoir is big enough, it doesn't really drop in pressure that much. And on average, this reg can just trickle away and just be supplying like the average flow rate of the pneumatic system. And it turns out that you need a very, very small reg if you have. So the buffer tank that's on the water test stand, it's like this big. It's efficient, I sized it correctly, and the reg has a CV of like 0.06. It's tiny. But it's not small enough for like a certain size relief valve, so I added this orifice here to restrict it even more, so I could go down a size in the relief valve. But you can talk to me if you want about the sizing for all that. This actually isn't on there right now, but we're going to sort that out. This, I just didn't have time to put the orifice on. So don't reg this up too far, because the relief valve won't be able to relieve the pressure, and you'll see that if you try. Yeah. Hoses. Read the Swagelock catalog. Swagelock is just great. Like, they have catalogs, and they don't just list the components; they list all of like this crap, like about selecting them, sizing them. One thing I would say is like hoses are great. You shouldn't use hoses like on the snake feed systems, like for everything. But they're great when you have machining tolerances. The water flow test stand is welded. There's no guarantee where those are going to end up. When you're fabricating tubing, it's not going to be exact. You can't just say like, I'm going to fix this component, and have a hard line in between, and it's going to work. It's not going to work out. You're not going to be able to either get the tube in, or you're not going to be able to tighten it down. So for things where components are fixed, or if there's some variability in where components are, then use a flex hose. Or if there's some movement, like Hydra on the rails, the engine slide on rails, we need that movement, and so a hose is great for that. But they're expensive. The materials aren't always ideal for like oxygen, say. They're pretty much expensive, and you can't just buy short sections because they're not very flexible. So hardline is needed like throughout, really, apart from in special circumstances. But there are other kind of considerations for mounting, which I'll get into. So read the Swagelock thing on hoses, it's good. A couple of quantities on flex hoses is the minimum bend radius. So it's basically the minimum allowable radius that you can bend, and that depends on whether it's in a dynamic or static situation. Again, the catalog says all that. It says in the catalog, actually, you should do this, bend in one plane. This is nice. This is on the water test stand. It's kind of doing this weird wiggle. It's not recommended, but fuck it. Check valves. The only thing I'd say about check valves is like sizing any valve, except for you need a certain pressure to open the check valve. It's called the cracking pressure. The Swagelock catalog has it all. And so just bear in mind, so for instance, on the water flow test stand vent line, it doesn't vent all the way to zero, and we're having problems with that because when we're filling up, we can't check the level accurately because there's still a tiny bit of pressure in there, and that's due to the drop, the cracking pressure of the check valves, which we're going to remove. Cryo considerations, not used cryos, but I know about a couple of things. very quickly just summarize like the boil off when you're loading something into from a cryo tank into like a room temperature tank. It's going to boil off. You're going to need relief systems. Pressurization. A cryo liquid will always want to sit at its boiling point. It's rising in temperature because it's sucking in heat, but as it boils, the latent heat of vaporization is stopping it, is like holding it at that boiling point. But the boiling point depends on pressure. So if you pressurize your cryo liquid, that boiling point rises, and now the cryo liquid begins to rise. Now all of a sudden, if you remove that pressure, then you're going to get more rapid boil off because now it's way above its boiling point. Now the extreme case of that is called a BLEVE. It's a boiling liquid expanding vapor explosion, and if this case is so extreme, then the whole liquid can just flash to a gas. So this happens a lot with like tanks, superheated tanks, either a cryo at room temperature or like propane in this case at if it's like there's fire impinging the tank or something, which was this test. If that difference between the boiling point when it's super hot and then you depressurize it is so big, then it does this huge blast. And there's a YouTube video here. Like this is a shockwave. Like literally, you can see it blast out. It's extreme. Another thing, like I've said, cryos boil off, and so anywhere where a cryo is trapped, it will boil off and it will increase pressure like a lot. And so cryo valves usually have these vents, and so it can't get trapped in this region here because when it's open, this region is just like a flow path. It's just in there. When it's closed, though, the seat in here can vent out to the upstream side. And there's a few different configurations, but that's just something to note if you're buying a cryo valve. It doesn't say cryo valve, but at least make sure it has a weep hole, which is what they're called as well. Fittings considerations, MPT sucks, but and don't use too many. That's basically what that slide says. CAD modeling, it's good. It's basically what that slide says. Learn how to route in NX. You guys use NX, so there's a great mechanical routing package, and this video basically tells you a lot of it. But videos like this, don't go and make tube as a part and put it in because you have to change it and it's an absolute nightmare, and then you can't do nice things like this. Like I tried to make a bent tube. I did make bent tube like parts for the water flow test stand, and then I just tore my hair out and learned how to do this, so learn how to do it. Mounting, so feed systems for hard lines, you're going to want it to go together and it's not going to be perfect, so use slots. So I have some examples here. This valve is mounted on slots. This one was a machining mistake, so it's bigger, but you can see it, so that's nice. Mount it in slots. These tanks on the water test stand are mounted with slots. Use hoses. These mounts from Swagelok go nicely on rails, and so, long story short, you want to see how your feed system is going together. So, like, explode it in your mind and bring the fittings together. You're going to want movement in those directions. Never constrain like your valves and stuff and then try and put hard line in between. It's not going to happen. But there's a lot of examples of that, like so this hose goes round and into the top of a tank. So I decided to have that flex. Then the tank can slide one way, and I have that in my mind, but then the valve can slide like in the other direction perpendicular to the tank. So the line between the valve and the tank like has those two kind of degrees of freedom. Just something to really consider in a system that you don't always need flex hose. So on the water test stand, you have those two tubes coming like out and bent round. Those are hard lines, but there is play designed into where the components are mounted. So yeah, I have something on testing, but I'm sure you're all familiar with leaking by this point. Yeah, and then I threw some slides in here for like sensors. So I would say, there's Omega symbol randomly, but I would say that instrumentation is like so important for feed systems, because if not, we're blind. And I don't know about you guys, but I've been quite confused with a lot of the data sets we've got from either firings or testing. And without data, if you just say, yeah, the engine fired or it didn't, obviously that's not going to tell you anything. So just make sure you respect all the instrumentation and make sure you have enough of it, but also don't trust what you get from the sensors. I know in the last firing, we accidentally flipped the PT lines, so we thought one pressure was another pressure, and so it was quite confusing. So make sure when you're censoring your feed system, make sure you thoroughly test it and verify everything, and that team do a good job of that. So I just have some examples of sensors. If you haven't noticed, this is how we integrate most of our sensors with the feed system. So we use these weld-on fittings. They work really well. We had a leak once, or 2 tiny leaks, but that was just on one fitting, I think, and it was just a poor welding job. So if you ever have one of these done, go tell Don to do the best job he can. He's a really good welder, but yeah, they work really well in general, and they're lightweight, and if it's not an extra connection, and the 1/8 inch ones, you can swage an actual thermocouple probe, and then we use these 1/8 inch lines, you'll see all on Hydra and the water test stand, to go to the PTs. Yeah, we're going to make it 3 minutes. So yeah, thermocouples. Omega is great for sensors. They have the configurator for thermocouples. It's a great little app. They also have one for PTs, I found. One thing I'd say on load cells is, which I suggest LPL starts doing, load cells give an output of millivolts per volt, and that per volt is per supply voltage. So if your supply voltage is off by 10%, your reading of load is going to be off by 10%. So I would suggest having one of the lines going into the NI and analog reading on the actual supply voltage. So you can just do that calculation in the post-processing and get precise load. I know for the water test stand, the load cell accuracy is important, so should do that. And then here, actually, all the rest of the slides are pretty much just data from firings. I was going to talk through. These data are from the blue steel firing, the kind of only semi-successful one we've had. So I did do a presentation way back when on all of this, but if you guys want to just reference this to look at what data from feed systems actually looks like, this is the ignition. So we have 2 minutes to go through this, but this is the oxygen coming into the injector, ramping up in pressure. Then this pressure increase here is in the fuel sensor, but the fuel hasn't been injected yet, but that's actually the oxygen coming into the chamber and backing up through the fuel side of the injector. So there's a little bit of pressure. This is the chamber pressure and the fuel side pressure, and then the fuel comes into the engine, and the purple is the engine pressure, and that's the engine starting. Then this here is water hammer, so that's before we open the valve slowly, so we get that ringing, that kind of oscillation as the pressure wave hits back and forth. You should be able to find out the length of the tube by the frequency there, but it was a kilometer when I figured it out, but you guys can do a better job with that calculation. But we're pretty sure that's water hammer. I just find this data really interesting. This is the engine pressures. I'm going to skip ahead to the here. So what we've been talking about is regulator droop. So this is the regulator pressures of the oxygen reg and the nitrogen reg. And this is when we open the valves, so the flow starts, and you get the seat load drop and the droop kind of in one. So this is how much the regs droop as the flow is flowing, and then we close the valves and it shoots right back up again. So that's pretty cool to see. And then they kind of vary because it's all a coupled system. Remember, the engine pressures are actually going down over the whole course of the firing because the nozzle is ablating. And that drop in engine pressure is different. It's causing differences in the pressure drop through the line, and it's affecting the pressures out the reg. So the data is so interesting to look at, I think, anyway. And here's the pressure in the tanks depleting over the firing, etc. So definitely, I would encourage you all to look at the data from this firing at least. hopefully we'll have more good data sets to come very soon. And then this is what we think is thrust. Lists. Yeah, well, that's another story. Then here's like water flow test and data, you'll find that in a paper. And finally, my lessons learned, which I did in like 2 minutes, but I'll rattle through them. Design for the worst eventuality, off nominal conditions, like don't just design for your flow rate, like what if this happens, what if the reg breaks, for the relief valve. Design to be fixed, to be like mended, to be fixed, like design it not to be like a maze to get into something, or to wrench. The Hydra, wrenching things on Hydra is an absolute nightmare. It should be raised up more or something, it's a pain. Design it to be tested, so materials, like IPA is going to be going in for testing, like what materials you need for that, pressures, proof pressures and stuff are going to be higher when you're testing, blah, blah, blah. So yeah, you'll have propulsion, but if you don't, then you can stick around and ask me questions. But that is it, 1 minute late, so thanks.